Hello, and welcome to Differential Equations. This is lecture 29, Eigenvalue Problems. Last time, we started talking about boundary value problems as opposed to initial value problems. This time, we're going to talk about families of boundary value problems. So recall that if A is an n by n matrix, then we say that a vector is an eigenvector of A with eigenvalue lambda if two things happen. V is not the zero vector, and A times V is equal to lambda times V. So in the same way, if L is a linear differential operator, we say that a function y is an eigenfunction of L with eigenvalue lambda if y is not the zero function and L of y is equal to lambda y. Right? If there is an eigenfunction, for a given eigenvalue, then there are infinitely many. And we refer to the set of eigenfunctions, well, really to the set of solutions of L of y equal lambda y as the lambda eigenspace of L, right? And we denote it eig sub lambda of L. Right? So just all of the y's, such that L of y is lambda y. More generally, we sometimes look for y's and lambdas satisfying that L of y is equal to lambda times w times y. So you should think of this w as being some weight function. In this case, we call these weighted eigenfunctions. Although in some books, you'll find that sometimes these are still just called eigenfunctions when the weight is implicit, right? So sometimes the weight will be clear from context, or the weight will just always be there, and these will just be called eigenfunctions, even though they're really weighted eigenfunctions. Okay, this is really only interesting when we also impose homogeneous two-point boundary conditions. So for example, for a second order operator, we impose y1, alpha 1 y of a plus alpha 2 y prime of a is equal to 0, and alpha 2 y of b plus alpha 2 y prime of b equal to 0. Right, so why is that? Well, the problem with not imposing boundary conditions is that you get too many eigenvalues and eigenfunctions. So for example, if L of y is, just take two derivatives of y, and we don't impose any boundary conditions, then every scalar lambda is an eigenvalue of L. Since L of y equals lambda y is the same as asking y double prime is equal to lambda y, right? Which is the same as asking that y of x be well, if lambda is equal to 0, you would just get a plus bx. And otherwise, you get a linear combination of e to the lambda, square root of lambda times x plus e to the minus square root of lambda times x. Right? So in this case, we found non-zero functions for any lambda, right? So then every lambda is an eigenvalue, and so that doesn't tell us very much about this operator. Right? Finding eigenvalues and eigenfunctions is a lot more interesting with boundary conditions. So for example, suppose we want to find all eigenvalues, eigenfunctions of L given by taking, so minus taking two derivatives, subject to the boundary conditions y of 0 equal to 0, y of L equal to 0. And here L is just some positive constant. Right, so here we're looking for all of the scalars lambda such that the boundary value problem minus y double prime equals lambda y with boundary conditions y of 0 equal to 0, y of L equal to 0 has the solution other than the 0 function. Right? So of course, this problem always has a solution if you allow the 0 function, because our homogeneous boundary conditions are met by the 0 function, and the 0 function would just make both sides of this equation equal to 0. So there's always that solution, right? Which means that it's not very interesting. Instead, we want to know, well, when are there non-zero solutions? And that's going to limit the lambdas that show up. Okay, so here, this equation is very easy to solve in general. It has characteristic equation. R squared plus lambda equal to 0, which has roots square root of minus lambda minus square root of minus lambda. So we will consider 3 cases. Right, depending on the sign of lambda. Lambda could be negative, it could be 0, or it could be positive. We could also consider complex lambda, but for the moment, we're just going to stick to real lambda, and later we'll talk more about that. So first case, what happens if lambda is negative? So let's say that lambda is equal to minus mu squared with mu a positive number, right? So then that would make these r's equal to plus or minus mu. So here y would be a linear combination of e to the minus mu x and e to the mu x. Right, then we need to impose our boundary conditions. So y of 0, which would be a plus b, we need that to be 0. And then y of L would be a e to the minus mu L plus b e to the mu L. And we also want that to be 0. So from here, we get that, say, a is equal to minus b. And so let's write that. So here, a is equal to minus b. And then if I plug that in over here, substitute minus b instead of a, then here I would get a times e to the mu L minus e to the minus mu L equal to 0. Now, that means that either this is going to be 0 or b is going to be 0, right? So let's think about this. When is this equal to 0? Well, it's equal to 0 if this is equal to this, right? But e to the something is equal to e to that minus something only if that something is 0, right? But mu and L are both positive. So this exponent is not equal to 0, which means that this difference is not equal to 0. So this tells us that b is 0, and then that first equation tells us that a is 0. So not an eigenvalue. Right? So we saw that if lambda is negative, then once you impose the boundary conditions, the only solution you end up with is the one where a and b are both 0. So it's just a 0 function. So that means that lambda was not an eigenvalue. Right? Second case, what if lambda is equal to 0? Okay, well then our equation is just 2 derivatives of y is equal to 0. So in this case, y of x would be a plus bx. Right, so if we impose our boundary conditions, y of 0 would just be a, and that would be 0. And then y of L, well, if you already know that a is equal to 0, that would just be b times L, and that's supposed to be 0. But L is positive, so that tells us that b is equal to 0. So we found that a is 0, b is 0, so not an eigenvalue. Okay, so our only possible source of eigenvalues is this third case where lambda is positive. So lambda is positive. Let's say lambda is equal to mu squared with mu positive, so that the roots of the characteristic equation are plus and minus I times mu, and so the general solution to the equation is a times cosine mu x plus b times sine of mu x. So now let's plug in our boundary conditions. Y of 0 is equal to 0. Y of 0, well, cosine of 0 is 1, sine of 0 is 0. So y of 0 is a, and that's equal to 0. Then y of L, okay, well, we already know a is equal to 0, so we can just ignore this term. So when we plug in L, it's this. So b times sine of mu times L equal to 0. So then either b is equal to 0, which is not interesting. Right? It's not interesting because if b is equal to 0, we already know a is equal to 0. So that would mean that y is equal to 0. And so that would mean that lambda is not an eigenvalue. So that's not the case we care about. Fortunately, there's another possibility. Sine of mu times L could be 0. Right? So since mu is positive, that means that mu would be an element of, well, pi over L, or 2 pi divided by L, or 3 pi divided by L, or generally just n times pi over L, where n is equal to 1, 2, so on. Okay, excellent. So we finally found some eigenvalues. Thus, the eigenvalues are the lambdas, right? Lambda was equal to mu squared, so this would be n squared pi squared over L squared, with n going through 1, 2, 3, and so on. And the eigenspaces, so this would be n squared pi squared over L squared, are just multiples of sine of n pi over L x, where we're taking arbitrary coefficient. Okay, perfect. So there's one example where we worked out what the eigenvalues are. So before we do another example, let's talk a little more about motivation, right? So why might we want to find eigenvalues, eigenfunctions of L? Well, one reason is that just as for matrices, finding this eigendata is like uncovering the hidden structure of L. It's a key step towards understanding L mathematically. There's a whole part of math called spectral theory that's devoted to understanding eigendata. The eigendata is usually referred to as the spectrum of the operator, a term introduced by Newton when he was studying the way light is split by a prism. A more practical reason is that eigendata of ordinary differential equations show up when we study partial differential equations. For example, later we will discuss a model for the diffusion of heat. If U is the temperature of a rod placed along the interval 0 to L, then a reasonable evolution equation for U would be that the derivative of U with respect to time is equal to the second derivative of U with respect to position. Okay, so that equation can be complicated to solve, but we could make the simplifying assumption that U of x comma t is a product, say capital X of little x and capital T of time, then this equation becomes, well, on the left-hand side, we're taking the derivative with respect to t. But if we make the simplifying assumption that this is the product of a function of x and a function of t, then this derivative only hits the function of t, right? So this would be capital X of x, t prime of t. And here, when you're taking derivatives with respect to x, well, those derivatives don't do anything to the t factor. They only hit the x factor. So you would end up with capital X double prime of x and capital T of t, right? And then one thing we could do, right, assuming neither of these functions is 0, because that would not be an interesting solution to this heat equation, we could put all of the t's on one side and all of the x's on the other. Okay, and now we stare at this equation. Notice that the left-hand side doesn't depend on x. And the right-hand side doesn't depend on t. So both sides must be constant, right? Because if this doesn't depend, right, this obviously doesn't depend on x, which means that this cannot depend on x because it's equal to this, right? But this also doesn't depend on t, so it doesn't depend on anything. So it must be constant. And by the same reasoning, this must be constant. Right? So if we call this constant lambda, then we can rewrite this equation as t prime of t over t of t is equal to lambda, and so is x prime of x divided by capital X of x. Right? So in particular, capital X satisfies that if you take two derivatives, you get lambda times the function you started with. Right? So there you go. We start with a partial differential equation. We assume that our solution has this particular form. This is called separable, right? Because it's a product of, we've separated it into a product of a function of x and a function of t. And then it turns out that these two functions satisfy this equation. So in particular, an eigenvalue equation. In this setting, if we assume that the rod's endpoints are kept at the fixed temperature 0, then capital X satisfies this eigenvalue equation with x of 0 equal to 0 and x of L equal to 0. And so we end up with essentially the same eigenvalue problem as above. Right, essentially the same because up above, I chose to put a minus sign in front of the second derivative. I like that choice because then it means that the eigenvalues end up being positive. And I prefer to have positive eigenvalues than negative eigenvalues. This is actually something that comes up a lot in differential geometry, which is sort of math I do. Taking the minus sign in front of the second derivative is known as the geometer's Laplacian. If you take the usual plus sign, then it's called the analyst's Laplacian. Let's do another example. Find all eigenvalues eigenfunctions of L given by minus a second derivative subject to y prime of 0 is equal to 0, y prime of L is equal to 0, where again, L is a positive constant. So as before, we're looking for all scalars lambda such that minus a second derivative of y is equal to lambda y prime of 0 is equal to 0, y prime of L is equal to 0. So this is the boundary value problem we want to solve. And we want to find all of the lambdas where you have a non-zero solution. Okay, so again, the characteristic equation r squared plus lambda equal to 0 has solutions r is equal to plus minus the square root of minus lambda. So we again consider 3 cases. Case 1, lambda negative. So I'll write it as lambda is equal to minus mu squared with mu positive. So here y of x is a e to the mu x plus b e to the minus mu x. And our 2 boundary conditions, y prime of 0 would be mu times a minus b, right? We want that to be 0. And then y primed at L, so this would be mu times a e to the mu L minus b e to the minus mu L, right? And we want that equal to 0 as well. Okay, so this first equation tells us that a is equal to b, and if you plug that in here, then you can pull out a or b as a common factor, and then you get e to the mu L minus e to the minus mu L, right? So as we talked about a moment ago, e to the mu L is never the same as e to the minus mu L unless mu is 0. So that's not going to be 0. So from here, we conclude that a has to be 0 and b has to be 0. So lambda is not an eigenvalue. Case 2, lambda equal to 0. Right, so then again, our equation becomes y double prime is equal to 0. So that means that y has to be a polynomial of degree of most 1. And then if we plug in our boundary condition, y prime at 0 is b, so that's 0. Y primed of L would be, again, b equal to 0. So we can satisfy the 2 boundary conditions by just getting b equal to 0, which means that there is a non-zero solution to our equation, just a, where a is any non-zero constant, right? So lambda equal to 0 is an eigenvalue, and the corresponding eigenspace consists of all constants, call them a. Okay, case 3, when lambda is positive, so let's say lambda is equal to mu squared with mu positive. Right? So y of x would be a cosine mu x plus b sine mu x. And the 2 boundary conditions, y primed of y prime of 0 would be mu times, so when I take the derivative of cosine, I get minus sine, and when I take the derivative of sine, I get cosine. If you evaluate at 0, then sine is 0. So that means that this term is not going to contribute, but this term will. So we end up with mu times cosine mu x. Mu is 0, so cosine of 0 is 1. So we just end up with mu b, and this is equal to 0. So mu is positive, which means that b has to be equal to 0. So when we do our next boundary condition, we can ignore this term because b is already equal to 0. So y prime of L is going to be a times mu, actually with a minus sign, minus a times mu times sine of mu x. And we need this to be 0. So either A is equal to 0, which is not interesting, or sine of mu x, sorry, that's not x, that's L. Sine of mu L is equal to 0, which, since mu is positive, implies that mu is pi over L, or 2 pi over L, or 3 pi over L, so on. So n pi over L, where n is 1, 2, and so on. Right? So we found eigenvalues that look like this, n starting at 1, and also the eigenvalue lambda equal to 0, right, which we could include here by just letting n be equal to 0. Thus, the eigenvalues are lambda equal to n pi over L squared, with n starting at 0, and the eigenspaces corresponding to n pi over L squared are just multiples of cosine mu is n pi over L x, where A is arbitrary. Right? Notice that I'm also including the case n equal to 0 here, because we found that that was just multiples of 1, right? But cosine of 0 is equal to 1. So this gives me the eigenspace both for the positive eigenvalues and the 0 eigenvalue. Okay, notice that we ended up with almost the same eigenvalues in this example as in the previous example, right? For when we were imposing y of 0 equal to 0, y of L equal to 0, then we ended up with these eigenvalues. And instead of cosines, there we had sines. Here we have cosines instead of sines, and 0 is an eigenvalue, which it wasn't before. But otherwise, it's a lot like the previous one. Okay, let's do a slightly different example. Suppose we want to find eigenvalues and eigenfunctions of L, and let's take minus the second derivative. But then to mix things up, let's also add 2 times the first derivative. Right? And subject to, let's take y prime of 0, 0, and y primed of pi is equal to 0. So here, instead of having an arbitrary endpoint L, I'm going to go ahead and choose that L to be pi. So we're looking for scalars lambda such that the equation minus y double prime plus 2y prime equals lambda y, with boundary conditions y prime of 0 equal to 0, y prime of pi equal to 0, has a non-zero solution. Okay. The characteristic equation here would be r squared minus 2r plus lambda equals 0, which I can rewrite as r minus 1 squared is equal to 1 minus lambda. And so it has roots 1 plus or minus square root of 1 minus lambda. So again, we'll consider three cases. But these cases will be 1 minus lambda positive, 1 minus lambda equals 0, and 1 minus lambda negative. Okay, so first case, 1 minus lambda positive, right, which is the same as saying lambda less than 1. Again, it's useful to introduce a mu just to have fewer square roots floating around. So let's say that 1 minus lambda is equal to mu squared with mu positive. So then the general solution before we impose the boundary condition looks like a times e to the 1 plus mu times x plus b e to the 1 minus mu times x. Okay, and the boundary conditions we want to impose, y prime of 0 should be 0. So what's y prime of 0 here? Well, that would be a times 1 plus mu plus b times 1 minus mu equal to 0. And our other boundary condition, y prime at pi should be 0. So what's y prime at pi? Well, it would be a times 1 plus mu times e to the 1 plus mu pi plus b times 1 minus mu e to the 1 minus mu times pi, right? And that should be 0. Okay. So what we could do here is, well, we could use linear algebra, for example, rewrite this as a matrix valued, coefficient matrix times our unknown vector equal to the 0 vector, right? And here we know that if the determinant is non-zero, then there's a unique solution. The determinant here is 1 minus mu squared times e to the 1 minus mu times pi minus e to the 1 plus mu times pi. And this vanishes if, well, the first factor would vanish if mu is equal to 1 or mu is equal to minus 1. But since mu is, by definition, positive, this case we don't care about. Or if e to the 1 minus mu pi is equal to the e to the 1 plus mu pi. Right, but this only happens if 1 minus mu was the same as 1 plus mu, right, which only happens if mu is 0, but in this case mu is positive, so that also cannot happen. Which means that the only case here is what happens if mu is equal to 1. Right? If mu is equal to 1, then y of x would be equal to a e to the 2x plus b. And if we put in our boundary conditions, right, since they both involve the derivative, this term would vanish when you take a derivative, and so you're just going to get that a is equal to 0. Okay, so this does correspond to an eigenvalue. Notice that if mu is equal to 1, right, put 1 here, that tells us that lambda is equal to 0. is an eigenvalue, and the eigenspace is just a constant. So here was B with B arbitrary. Okay, that was case one. Case two, right? Case two is 1 minus lambda equal to 0, right? So that's say lambda is equal to 1. Right, so here the characteristic equation is r minus 1 squared equal to 0. So that means that our general solution is a multiple of e to the x and a multiple of x times e to the x. Right? Let's impose our boundary conditions. So y prime of 0 would be a plus b, and y primed at pi would be a e to the pi plus b e to the pi times pi plus 1. Right? So here, this would tell us if this is equal to 0, then a is equal to minus b. So then this would come down to b times pi times e to the pi equal to 0. So that tells us that b is equal to 0, and then this previous equation tells us that a is equal to 0. So this is not an eigenvalue. Okay, and so that leaves us with case 3, 1 minus lambda negative, right? Which is the same as saying that lambda is greater than 1. And so here we'll say that 1 minus lambda is equal to minus mu squared with mu positive. So that makes y of x equal to a e to the x, sorry, e to the mu x. No, sorry. Just let's scroll back up. So the characteristic equation has roots 1 plus minus square root of 1 minus lambda. So if you put 1 minus lambda equal to minus mu squared, then you're going to have roots 1 plus minus I times mu, which means that the general solution is going to be a e to the x cosine mu x plus b e to the x sine mu x. Okay, so let's impose our boundary conditions. I'm going to start by just computing what is y prime of x, just to have this around. So, well, you're going to have an e to the x as a common factor when you hit that. So you're going to have an a plus b mu times cosine of mu x. And then you're going to have b minus a mu sine of mu x. Okay, so y prime of 0 would be, okay, this would be 1. Then at 0, cosine is 1 and sine is 0. So we would just end up with a plus b mu equal to 0. And y prime of pi, so this would be e to the pi times a plus b mu. Well, a plus b mu is, we've just checked as 0, so we can ignore that term. We're just left with this b minus a mu sine of mu times pi, right, equal to 0. And so this tells us that a is equal to minus b mu, and if we substitute that here, we end up with e to the pi times b times 1 plus mu squared times sine of mu pi. So, right, this is not 0, and this is not 0. So either b is 0 or sine of mu pi is 0. Right, so either b is 0, which is not interesting, or sine of mu pi is equal to 0, right? Which, since mu is positive, means that mu is equal to 1, 2, 3, and so on. Thus, the eigenvalues for case 3 are, so the lambdas corresponding to these mu's, right? Lambda is equal to 1 plus mu squared, so the eigenvalues are 1 plus n squared, where n is 1, 2, and so on. And the corresponding eigenspaces would be b times e to the x times sine of nx minus n times cosine nx with b arbitrary. Okay, and then let me finish with a remark. In this lecture, we have only considered lambda real numbers. One could, and in fact should, also consider lambda complex. Fortunately, the operators L that we have considered here only have real eigenvalues. We will justify this next time when we'll go over a very important theorem in this business known as the Sturm-Liouville theorem. Okay, and that'll be next time.